Our next speaker is Professor Samriddhi Sankar from ICTS. He will be talking about spectral scaling in bacterial turbulence.
Let me begin by thanking Rahul, Ranjini, Kavita, Sanjib, Abhishek, and Prerna for getting all of us together for over 10 years now. So the reason, as you will see, this is really a high Reynolds number turbulence talk masquerading as a soft matter talk. That's and a sort of biophysics talk. That's because many of you in the audience are more familiar with the system, but all the tools and techniques that I will be using will be from the sort of perspective that I'm more comfortable with. So, okay, so what's the context? So the context sort of, begins for me with this sort of paper by Wensing et al., where they looked at suspension of subtilis bacterium in a quasi-2D setup. It was a dense suspension, and when they imaged it very nicely, it sort of reminded one, so this is really at low Reynolds number, but when they image it, it reminds one of two-dimensional turbulence, something that you might see in a soap film, which is agitated and is at very high Reynolds numbers. And this sort of gave rise to this sort of area of active turbulence and essentially the fact that the dynamics of these systems kind of are reminiscent of vertical chaotic high Reynolds number fluid turbulence. So how do we begin to model? So this is, for example, a movie from an ongoing experiment in Shashi's lab over at NCBS with E. coli bacterium. So when they're densely packed, one of the macroscopic approaches is to write down essentially a coarse grain velocity field, and that's a sort of, and you end up with equations which look suspiciously close to the Navier-Stokes equation. And essentially you can solve these equations, and you can sort of argue that what you see on the right-hand side looks deceptively similar to what you see on the left-hand side, which is in the real experiments. So in this talk, in the next 3 or 4 minutes, I will be treating these bacterial suspensions as a continuum two-dimensional fluid. And the question that former postdoc here, Siddhartha, former PhD student Rahul and student Martin James were really asking is, in what sense are these low Reynolds number flows turbulent? So as I said, this is really a turbulence talk, but using the crutch of these systems. So essentially, what does it mean to be turbulent? So for inertial turbulence, which is high Reynolds number flows, one of the things that people know since the time of Kolmogorov and going a little further back is that if one were to measure this object, which is known as the energy spectrum, which is essentially just the UU correlate in Fourier space, it has a power law scaling delta. And what people find is that independent of what sort of experiments you do, what sort of Reynolds number you have, whether it's a wind tunnel or a washing machine, you always end up with an energy spectrum which has a intermediate sort of asymptotics where there's a power law scaling, and the scaling, the exponent of that power law is the famous sort of Kolmogorov 5/3 result, and that's independent of everything in the system, including Reynolds number. What people showed a few years ago was that when you play the same game with these sort of low Reynolds number suspensions with the equations that I described, you end up seeing power laws. You do get a power law in the spectrum, but the exponent varies as you keep changing activity, as you feed your bacteria with more energy, etc. Right? So such studies do show that bacterial suspensions, if this is the yardstick, are not really turbulent in the sense that you do not have a universal scaling form. So what we show in this work is that there is an approximate scale invariance which emerges with a universal scaling exponent when you push these suspensions beyond the critical activity. Right? So I won't go through the calculations, but in a couple of minutes, I'll just summarize the result. So essentially what we do is you again begin with the definition that I pointed out. You take these the equations of hydrodynamics for these suspensions, and then, and this we can discuss over lunch, but then you massage these equations and use several levels of approximations, which are known in the business as the quasi-normal approximation, and you essentially close the hierarchy of higher order moments at the second order moment, make suitable definitions on how to do it, and this is really in case you want to sort of grab me with the details of the calculation. And then once you do that from these equations, just from pure theory and analysis, what you find is when the activity is low, you get an energy spectrum with an exponent which indeed depends on the activity, right? So there's nothing universal when the activity is low. When you have, so the question is how low is low? So what one can argue is, if you stare at this form carefully, that when you push alpha towards a critical value, this exponent gets close to zero. You remember the slope from the Bratinov paper. The effective timescales in the problem are no longer constant. And then, lo and behold, you put all of that in, and then you end up getting an energy spectrum, which is k minus 3/2. So the essential point is, without worrying too much about the nitty-gritties of the calculation, the essential point is one can theoretically predict an alpha C of -5, around -5, where for activity lower than that, you have a non-universal scaling behavior of the spectrum. For things which are much more active, you get a constant k minus 3/2. So that's the analog of the k minus 5/3 in the Kolmogorov picture. So this is really the last slide. So so essentially, with all these approximations, are these exponents valid? So we did a full numerical simulation of the original equations with which we began, where we can measure the spectrum and the spectral exponents carefully. And what we find, so these are measurements from simulations, where we indeed find that this analytical prediction that at around alpha C, it crosses over and stays put at -3/2 is indeed valid. So the bottom line is that bacterial flows beyond this critical activity indeed become much closer to inertial turbulence if the only definition of inertial turbulence is universality of scale invariance and exponents. So just to conclude, and I'm well within time, is that there is an emergent universality in the scale invariance of active turbulence, and we haven't talked about this, but happy to discuss, and this is sort of accompanied with the onset of intermittency, again, something that high Reynolds number people are very fond of discussing. And we do find these sort of states beyond alpha C. But it still sort of begs the question, and there are some other stuff which is going on in the group, is whether active turbulence really is like fluid turbulence, because I've just used one sort of yardstick to address these questions. So with that, I'll stop, and some of the references for details, and I'm around, of course. Yeah, thank you.
Questions?
There's something I don't understand about scale invariance in this problem. Yeah. The velocity field in this problem, because there is a damping even at zero wave, damping or pumping at even at zero wave number, isn't a conserved thing. There's no, is there anything that's conserved, or is the incompressibility constraint important?
The incompressibility...
There must be something singular at small wave number.
Right, so the incompressibility condition becomes quite important, and that's a little fudge, as you know, where one assumes a very dense suspension. So
that's okay, but at least at the level of the calculation, incompressibility is crucial, right? Okay, so maybe
and that allows us to define a flux and, use the usual,
all right, great. Thank
game
you.
that we play.
Let's thank the speaker once again.
Thanks.
Our next speaker is Sikal.